Hello, this is a lecture series for Chemical Engineering Thermodynamics 1, and we are currently at lecture 4b. For lecture 4a, I introduce the second law of thermodynamics, and together with the spontaneity with the direction of the process. During the derivation, there's one parameter called entropy coming up, and mathematically the second law said that the spontaneous process would take place only when the entropy of the whole universe is increased. So for this lecture, for lecture 4b, we will focus our attention on how to calculate entropy change. Okay, for this lecture, as I said, we will focus mostly on the calculation of delta S. Just to make it easier to see, let us divide or classify problems into different scenarios. The first one is the change in entropy for the system containing only one species, one single phase, and no reaction. Within this kind of system, the degree of freedom is equal to 2, just like what we repeatedly mentioned this in lecture 2 and lecture 3. As the degree of freedom is 2, that means we can write entropy as a function of two variables. For entropy, this is a little bit different than what we previously discussed. In lecture 2, I mentioned that if we deal with enthalpy, H, usually we will pick temperature and pressure. But when we deal with the internal energy, we usually pick temperature and volume. Okay? But for entropy, we can do either temperature pressure or temperature volume. Let me show you the way. If I pick to represent entropy as function of temperature and pressure, according to calculus, we can expand the differentiation of entropy into two terms. The first term is differentiation with respect to temperature at constant pressure here, and then the other term would be partial differentiation of entropy with respect to pressure at constant temperature. Okay, and once again, we can further derive this equation using what we will learn in lecture 5a into what we can measure. Okay, the first term can be converted into heat capacity over temperature dt, subtracted by this term, partial differentiation of velocity with respect to temperature at constant pressure. And you see from the form of this equation that this particular differentiation can be further derived using relationship between temperature, pressure, and volume, which is basically equation of state that we learned in lecture 3a. Okay? In another way, if we pick temperature and volume, we can write entropy as a function of temperature and volume and use calculus to expand them into two terms. The first term is represented by this term, changing with entropy at constant volume, and the other term would be differentiation of entropy with respect to volume at constant temperature. And once again, if you derive it further, you can get this relationship. As you can see from these two equations are written in form of measurable variables. Unlike internal energy and enthalpy, if you pick internal energy to be written as temperature and pressure, then when you do derivation, the right hand side will be something that cannot be measured. The same thing applies for enthalpy if you write enthalpy as a function of temperature and volume. But for entropy, either way you end up with whatever on the right hand side are measurable. So we can use these two functions depending on situation that we have in hand. Okay, so the most question asked about these two equations is when will we use the first one, when we will use the second one, or which one is easier to use. Let me show you the way first. if we consider the first equation, this equation, it is written as a function of temperature and pressure. So it is easier to visualize the process by plotting the process state onto the temperature and pressure graph like this. So let's start with the initial state at temperature 1, pressure 1 here with entropy of S1, changing by any means to end up with temperature 2 and pressure 2 with entropy S2. So the process takes place along this red line, and in general this red line can be reversible, can be irreversible, can be any way. Okay, so we want delta S, which is S2 subtracted by S1. From this form of the equation, if you notice, the first term is differentiated with respect to temperature here. So the variable in front of this is a change at constant pressure. So that means the first term can be represented using this blue line. It's a change at constant pressure P1 here to this point. Okay, changing only for the temperature, and when you integrate it with respect to temperature change T1 to T2, that corresponds to the first term in this equation. So let's call this delta S1. Then if you change further from this point to the end of the process at T2 and P2, this change takes place at constant temperature T2 by changing pressure from P1 to P2, which corresponds to this term. The first term, the parameters here, is a change at constant pressure, and then you integrate it with dP. So therefore this term can be found basically by using this path. If we call this path to be delta S2, this particular term represents delta S2. Okay, so if you know Cp and you can find equation of state that is suitable to find dV by dt, using this particular form of equation can lead you to delta S of the process. On the other hand, if you pick this one, it would be hard to visualize the data from PT plot, because the integration in the bottom equation here requires integration with respect to volume. So you need to imagine that you start from the initial state point 1 here with T1, P1, V1, and then end up with this final state T2, P2, and V2. Okay, so the initial and final state are still the same, but the way we calculate it will be a little bit different. So in order to visualize it easier, it would be preferable to plot volume with respect to temperature. Okay, so at initial state, from this plot we have low pressure 1. Pressure 1 here is low. Okay, so if the pressure is low, normally the volume will be high. You have higher molar volume. When you somehow increase the pressure, your system would be somehow compressed and molar volume supposed to be lower. So if you plot within P volume temperature plot, the initial plot would be up here and the final state would be down here, and the process path would be drawn like this. Okay, so once again the delta S in this plot and delta S in that plot are essentially the same. But the way to visualize it, if you use this equation, the first term is integrated with respect to temperature, so it means that you change from initial state by means of changing temperature under the condition of constant volume. Okay, so it's going under the condition of constant volume from here to there. If delta S here is called delta S3, this particular term is essentially delta S3. And then from this point to the final state, you just fix the temperature. Here, this term was found basically from the change at fixed temperature, and you integrate it with respect to volume. So you're changing from volume V1 to V2. This change corresponds to delta S4, and therefore this is delta S4. Okay? Please understand that delta S1 here and delta S3 here are not the same. Even though the integration is done with respect to the change in temperature. But if you notice, or if you look closely, you see that this is heat capacity at constant pressure, and this is heat capacity at constant volume. They are not the same. Although they are related, but they are not the same. So after integration, the first one, delta S1, is an integration under the assumption or under the path of constant pressure, this path. But for this term, the integration is done under the constant volume path. So they are not the same. Please be sure that you understand that delta S1 and delta S3 are not the same. Okay? Now the next question would be, which form should be used? Again, it depends on many factors. The very first and obvious factor is which kind of data that you have in your hands. If you have CP, then it is easier to use the top equation. If you know CV, then it is easier to use the second equation. But some of you may ask, can we use the relationship between CP and CV, just like CP equal to CV plus R, and change from CV to CP or CP to CV accordingly? The answer is yes, you can in some certain criteria. For instance, CP equal to CV plus R is applicable only for ideal gas. If your system is not ideal gas, then they are related in different manner that you may or may not know. Okay? Then the conversion from CP to CV for non-ideal gas may be difficult, may be so difficult that picking up the data of CV is easier than picking up the data from CV, for instance. So the former equation depends on the data that you have in your hands. Secondly, if you consider the second term here and there, it requires differentiation. So if you use simple equation of state, for instance, ideal gas law, finding either term is equally simple. But if you use more complicated form of equation of state, for instance, if your system is a high pressure gas that cannot be represented by ideal gas law, then you need something more complicated. If you pick cubic equation of state, pressure will be written on the left hand side and volume will be written on the right hand side as volume to the power of 3. So finding differentiation of pressure will be relatively simple. On the other hand, if you try to find dV by dt using cubic equation of state, you have to rearrange the equation of state so that you can write volume as a function of pressure and differentiate it subsequently, which will be more complicated. Okay? On the other hand, if you pick the simple equation like Pitzer equation of state that can be represented by in terms of volume equal to something, then you can take that differentiation right away without concerning how difficult the differentiation would be. So again, it depends on the data that you have on your hand. But essentially, you need to understand that these two equations must give the same answer. If you get different answer, that means you do something incorrectly or you made incorrect assumption. The other way that we can calculate delta S is using the definition of entropy change. From what we learned from Carnot cycles, delta S can be calculated based on Q reversible over temperature. But you have to notice that this particular relationship is applicable only by definition when you use the reversible heat. So if your process here, for instance, if Q associated with the process here is not reversible. If the red line, the process, the actual process that you consider is not the reversible process, if it is irreversible process, you need to find indirect path that is reversible. You have to draw the green line, which is indirect path from the initial state of your system to the final state of the same final state of your system, and find the reversible heat associated with the green line before you can use this Q reversible in this equation. Okay, so one complication using this definition would be you need to make sure that the path that you are going to use for this definition, the path must be reversible. Okay, the other complication comes from temperature here. You see from this relationship that temperature seems to be constant, but in our actual system the temperature might not be constant. For instance, in this particular examples, temperature is changing from T1 to T2. So which temperature should be used here? Okay, if you use T1 directly or use T2 directly, the calculation will be wrong. You need to create another path which is reversible and isothermal here before you can use this equation. So in general, these two equations are sometimes more preferable. Okay, so what we discussed earlier using this function or that function in general can be applied to any system, but most of the time we consider before and after change. So sometimes we think that it is applicable for closed system. What about open system? How can we write the equation for open system? If you recall what we did with enthalpy or internal energy or energy balance in general, normally we said from lecture 2 that if we pick the system to be closed system, we can write delta U equal to Q plus W, although that equation can be applied to either open or closed system, but it is preferable for closed system. For open system, we develop another equation suitable for open system. In that case, we convert internal energy into enthalpy and use that as if that equation, which is M times enthalpy times kinetic energy times potential energy and so on, that equation were developed for open system. The question would be, can we derive something like that for entropy? Okay, if we consider the open system, the structure of open system, we will have input, the flow rate of fluid going into the system here, and then we have output in general, and we draw the system boundaries as a dotted line. Along the way, you may have the transfer of energy into the system by heat or work. For open system, the work that we will consider would be the shaft work. Okay, please note that both Q and W would have the dot on top. That means this is the rate of energy transfer in the unit of joule per second or energy per time. Again, the system can be at steady state or can be unsteady state in general. If the input is of the mass over here has the entropy of S1, and S1 should have the unit of joule per mole or kilogram Kelvin. At the output, the entropy would be S2. Can we write entropy balance in the same manner as what we developed for energy balance? The answer, the theoretical answer would be no. There's no such thing as entropy balance, simply because entropy is not conserved. Unlike energy, in energy we can say that when we convert or when we transfer energy from surrounding into the system as heat like this, energy of the system would be increased while energy of the surrounding would be decreased by the same amount of energy transfer. Okay, so let's say we have the transfer of energy here by 100 joule. The surrounding would lose 100 joule. The system would gain 100 joules. So change in energy of the system would be plus 100 joule. Change in the energy in the surrounding will be negative 100 joules. That number can be written like that because energy is conserved. You cannot create energy and you cannot lose energy. But for entropy, that's not the case. Okay? When you change entropy in the whole universe, let's say you have the increase in entropy in the energy in the system like this, it doesn't mean that that amount of entropy increase comes from surrounding. Okay, it can be generated anywhere in the system. So therefore entropy is not conserved. You cannot say that this amount of energy or amount of entropy created with or increased within the system comes from surrounding only. It can be generated within the system too. So this is inequality. Okay, the increase in entropy of the system is not essentially the same, or is not necessarily the same as a decrease in entropy of the surrounding. Instead, we can say that the increase of entropy in the whole universe here can be divided into two regions. First will be the increase of entropy within the system, the white area here, and the next one will be the increase in entropy in the surrounding. So let's say we have plus 50 unit of entropy increase in system, and then plus another 20 units in the surrounding. Therefore, the total entropy change of the whole universe will be 50 plus 20. Something like that can be written or can be mentioned. Okay, but this particular equation is not conservation of entropy at all. But if we rely on this relationship and saying that for the sake of derivation here, if S2 is greater than S1, let's say we have increase in entropy of the mass going out of the system like this. How can entropy be increased? Okay, so let's consider the entropy generated within the system first. Okay, so you have output entropy to be greater than input entropy. So there must be the generation of entropy somewhere. The difference between entropy going out subtracted by entropy going in here is just like when you have more money leaving somewhere than before you entering. Let's say you have if you walk into the casino and going out you gain money than going in. So that means the amount of money going out and subtracted by amount of money going in, that would be your benefit, right? That would be your profit. So this is the same thing. These two terms subtracted from each other is essentially telling you how much entropy is generated. Okay, so mass flow rate times specific entropy of the outlet subtracted by those of the inlet. That would be the amount of entropy generated within the system. These two consider all kinds of entropy increase by any means. So these two terms do not care how entropy will be generated. It just tells you that after passing through the whole system, you gain some entropy, but it does not tell you how. So it doesn't matter whether it's increased by heat or increased by reaction or by any means. They are all taken care of. Okay? So I can say that these two terms represents the increase of entropy within the system by all means. Once again, you have to consider that whatever pass into the system gain entropy. Okay, just like this box, the pink box, the flow rate entering the system can go anywhere they like, any pattern of the flow and then going out. Okay, so these two terms represents this amount of entropy within this box, this pink block. So you have the mass going in. Along the way it gains entropy, and at the outlet you can see that the entropy of the pink block is increased by this much. Alright, so I can say that these two terms representing the increase of entropy in the flowing part. Okay, however, in addition to the pink part, the system itself can also generate entropy. For instance, if the system has not reached steady state, the system itself can expand. It can change the volume. Expansion like that, the changing in volume like that, may be associated with the increase in entropy as well. And that must be calculated in addition to entropy increase from the flowing part. So the white part here, the increase in entropy of the white part should depend on the mass of whatever white part contains. Okay, mathematically we say that the mass within the white area here is mass of the system. Please note that mass here has no dot on top, so this mass has unit of kilogram, but this mass flow here, m2 dot here, has a unit of kilogram per second. Okay, so flow here means how fast the mass is applied to the system, but mass system here is how many kilogram of mass are contained within this area. So this mass may change with respect to time if the system has not reached the steady state. If the mass is changed, therefore the total entropy around or surrounded by this dotted line may also be changed. So if it changed with respect to time, the total amount of entropy change can be represented by this term. Basically, the mass should have its own entropy. If you multiply by the specific entropy of the mass within the white area and differentiate it with respect to time, the whole term here tells you total entropy within the dotted area or within the white area that is changing with respect to time. That also represents the increase of entropy in the system. Okay, so the first term is associated with whatever flow in and out, but you should notice that in and out is in and out of the system, so we consider this to be the system part. This is also the system part. This is considered the dotted line here, whether it's expanding, contracting, and the change in mass within the dotted line is also associated with the change in total entropy of the dotted line. Okay, so the generation of entropy in the white part should be combined with generation of the entropy by the flowing part, and these two are called generation or increase of entropy within the system by all means. So once they combine, we don't need to consider effects of the heat here to the change in entropy within the white part anymore. Okay, because this heat has already been taken care of by the term entropy of the system here. Okay, so adding these two terms together means that we taking account of all entropy change in the system already by all means. So that means entropy change by the heat here is already included. On the other hand, for entropy change or increase in entropy in the surrounding, now it would be easier to understand if I flip this sign, okay, so that you can understand it's easier. If the system release heat to surrounding, normally we said that the mass of the surrounding are not changed. The surrounding are usually very large, the properties are not changing. Okay, but when system release energy to surrounding, and we learned from lecture 4a that heat can make the change in entropy, but work does not make any change in entropy, right? So we consider only heat here. The transfer of energy as heat from system to surrounding makes the entropy of the surrounding to be increased. So if you assume the temperature of surrounding to be constant, if you take the surrounding to be reservoir, even though you change anything in surrounding, the temperature does not change. You can use the definition of entropy. The increase in entropy, or delta S, can be calculated based on Q over temperature. Also, if you notice earlier, we said that Q would be reversible heat. So if you assume that the process of heat transfer from the system to surrounding, the transfer here is reversible. Again, let me say this one clearly. The heat transfer here is reversible, even though the change within the system can be or cannot be reversible. It doesn't matter. The change within the system may be irreversible, but if we assume that the heat transfer to the surrounding here, this particular transfer is reversible, then we can take this definition directly. Okay, we can make this heat to be heat of the surrounding here divided by temperature of surrounding to find change of entropy from the surrounding. And then in this case, we always treat that surrounding receive heat reversibly, as I mentioned. Okay, then we can convert heat of surrounding or heat received by surrounding to be related to heat of the system. Essentially they're the same thing, just different in sign. Okay, so if I convert this subscript from surrounding to system, I need to add negative sign over here. So this particular term is essentially the increase in entropy in the surrounding, and we take the increase by means of heat transfer only, because work is not associated with the change of entropy, as we mentioned in lecture 4a. So if we combine these three terms together and call the increase in entropy of the universe to be Sg dot, okay, this is rate of increase of entropy in the whole universe. By definition here, it can be divided into two parts, one from the system, the other one within the surrounding. So if you add them up, you get Sg dot to be written as the function here. If you modify this further or generalize the equation, in general system, you may have more than one input and more than one output. So you just take all the output entropy subtracted by all the input entropies, and then output subtracted by input can be represented by delta. So it is essentially delta ms. Okay, for heat transfer in the system, in the real system, you might have more than one heat transfer in the system. For instance, if you consider Carnot cycle, there's a heat transfer around hot reservoir called QH, and then another heat transfer around cold reservoir called QC. Around hot reservoir, QH is transferred and temperature of hot reservoir is TH. For cold reservoir, we have TC over QC over TC. So in that case, all heat transfer must be combined. So therefore, we put the sigma sign right there. So that means this is the heat transfer from the system to surrounding everywhere combined. Okay. To use this one, if you look at the meaning of Sg dot, this is the increase in entropy of the whole universe. And according to the second law, if the entropy change is positive, or if you have increase in entropy change of the whole universe, then the process is spontaneous. If you have the decrease of entropy of the whole universe, then the process is non-spontaneous. Okay, a little bit more, if it is zero, then it is spontaneous and reversible. If it is greater than 0, it is spontaneous, but it is irreversible. Okay? So we can use SG dot to determine whether the process in open system is spontaneous or not, just by looking at the sign of the SG dot itself. And SG dot can be found from this equation. But if you look at this equation, the form of this equation, it looks fairly familiar. This one is in and out term. It's a change of entropy, just like in and out. This one seems to be very similar to differentiation with respect to time of energy inside, or by this case, entropy inside. So this term looks like accumulation term, okay? And this term seems to be the transfer through the system boundaries. So sometimes some people look at this equation and take this equation as entropy balance. Okay, so I would like to emphasize that in theory there's no such thing as entropy balance, but the form of the equation we obtain can be written in similar structure as the balance equation. Okay, so in general, some people call this equation entropy balance, even though it has no theoretical basis. Okay, so for the next system is a system with reaction. This is very similar to what we calculate the heat of the reaction in lecture 2. During that time, we introduced the term heat of reaction. By this term can be calculated based on what we call heat of formation. Okay, using heat of formation of the product subtracted by heat of formation of reactant. Of course, you need to multiply by stoichiometry coefficient. Again, with just a reminder, this particular equation, the circle here, the superscript circle here, represents the standard condition, which is 1 bar. So pressure is signified by these signals or these symbols, while the temperature must be written as a subscript here. Normally, this equation is used to calculate the change in enthalpy at constant temperature and pressure. So in similar manner, we can write similar thing for entropy change of the reaction. So we can use entropy of the product subtracted by entropy of the reactant in similar manner as what we did for heat of reaction. The only thing that is a little bit different is that for enthalpy here, this is delta HF. But for entropy, this is just entropy. We can write entropy by itself because according to the third law of thermodynamics, entropy is absolute. But enthalpy here is relative. Okay? So since entropy is absolute, it is 0 at 0 degree Kelvin of the solid crystals. Then entropy, the absolute value of entropy, can be used here directly. Okay? Once again, the circle here represents the standard condition of 1 bar throughout the whole equation, and temperature must be specified as a subscript here. If you recall lecture 2b, this is an example that I show you in lecture 2b for the calculation of change in the enthalpy if the reactant here and the products are not at the same temperature. So we need to go along this red arrow here as the direct path, okay, and we consider that direct path, the red path cannot be calculated directly. It is more convenient to go indirect path by using the black line and the blue lines combined. So you get delta H of the process to be delta H at 25 degrees C, which is the black line, added by the change in temperature according to the blue lines. For entropy, we can do the same thing because entropy is also state properties in the same manner as enthalpy. So if you want to calculate entropy change when the reaction takes place and the reactant and the product are not at the same temperature, then similar process can be done. Delta S, the direct path, should be the same as the combination of the indirect path, in this case the black line and the blue line. However, the black lines here are essentially what we derive over here. Okay, it's just the change in entropy at the same temperature. And then the blue lines here is a change of each component under the change of temperature. Okay, so from here we change from 25 degrees Celsius to 300 degrees Celsius. We don't change the species, we don't change the phase. So this one comes to whatever we discussed first. It's a change of one single component in one single phase, changing only temperature. So S1 and S2 can be calculated using what we derived earlier, like this equation. Or you can also use the one, but this one is more convenient because you can see that the second term here is written as a change in pressure, but now this blue line has no change in pressure, so this term can be dropped. It is more convenient to use this form, written write down the S as a function of temperature and pressure. So S1 and S2 are essentially integration of Cp over T dt. Okay, so the same concept of indirect path can be applied to entropy calculation. Okay, however, entropy change of the reaction by itself is not quite useful, simply because according to second law, the change in entropy of the system only is not enough for the prediction whether the process is spontaneous or not. We need both delta S of the system and the delta S of the surrounding. Let me give you an example. This is a formation reaction of water, but it is not exactly formation of reaction because the coefficient here is 2. If we consider the formation of reaction, this number is supposed to be 1. Okay, so this equation, but however on the left hand side the reactants are single element, so it is very similar to formation reaction. If you look on the left hand side, both reactants, hydrogen gas and oxygen gas, are gases, but on the right hand side the product is a liquid. So we change from gas to liquid if we assume the conversion is done 100%. So that means you change from something chaotic. Gas has molecules which are traveling or moving around chaotically. Liquid, the molecules of liquid does not move that much. Okay, so you change from something more chaotic to something less chaotic, and we realize that entropy is an indicator of chaotic dispersion of mass and energy. So we expect decrease in entropy of the system. So delta S of the system is expected to be negative. Okay. At 25 degrees Celsius 1 atm, which can be considered as standard condition, then if you look up at the reference table, you can get entropy of hydrogen, oxygen and water as this number. If you take this equation and calculate change of entropy of the reaction, you can simply take the stoichiometry coefficient multiplied by entropy of each component or species, then take the product subtracted by those of reactants. Okay, punch in the number in your calculator, you get negative 327, which is what we expect, the negative sign. Please note that the unit here is joule per Kelvin. There is no mole here because we already multiplied by number of mole. Once again, at this condition of the reaction, if you find the heat of formation for all species in the system, then you see that the heat of reaction can be calculated based on 2 times of heat formation of water, because this simple equation is basically 2 times of formation equation of water. So just multiply it by 2 here, and you end up with negative 572 kilojoule. This negative sign means that the reaction is exothermic. In detail, it means that there's a heat transfer from the system to the surrounding. Okay? So at constant pressure, we learned from lecture 2 that the heat associated with the system at constant pressure is equal to delta H. So therefore, this amount of energy, 572 kilojoule, is transferred from the system to surrounding as heat. You can also write that heat is negative 572. So therefore, the surrounding receive this much energy. So heat of surrounding is 572. If you assume the temperature of surrounding to remain constant at 25 degrees Celsius, you can get the delta S of the surrounding like that. Punch in the number, is about 2000 joule per Kelvin. Okay? From these two numbers, you can find delta S of the whole universe. Just add the numbers together, you get positive number. So that means the reaction here is spontaneous. Okay? So even though the system entropy change is negative, by system, if you look at the system itself, it seems like the reaction is not spontaneous. But the chaotic dispersion of the surrounding is dominant here. So the reaction within the system released large amount of energy, so that amount of energy create a lot more chaotic movement in surrounding. So as a whole, when you consider surrounding and the system together, there's more chaotic in the universe. Okay, so that's why the whole process here is spontaneous. So I can say that spontaneity is a result from disorder in the surrounding. But a little bit more about this reaction. If the whole process here is spontaneous, how come we can still have hydrogen and oxygen in the atmosphere? Why don't we have them combine into water and rain down constantly? Okay? The answer is that in thermodynamics, what we predict here is just a tendency, whether the process is spontaneous or not. It does not tell whether or how fast the process would be. Okay? So thermodynamics can predict whether this process will take place eventually, but whether it will be fast process or slow process, you need engineering kinetics. Okay, you need to calculate kinetics of the reaction, and that would tell you how fast or how slow the reaction would be. Lastly, for the system with phase change, okay, we can calculate entropy change associated with it as well. Normally, the phase change occurs at constant temperature and pressure. For instance, if you boil water, the water would boil at 100 degrees Celsius under 1 atm. It doesn't matter how much liquid you have. As long as you have liquid water and water vapor together in the state that we call boiling, the temperature remains the same under the constant pressure. Okay, so the calculation is usually done under the assumption or under the constant temperature and pressure. So therefore, if it is constant temperature, it means that we can use definition of entropy. So delta S would be reversible heat over temperature, and again this temperature remains constant. If you consider system temperature, T system will be constant. If you consider that system, the phase change system, to be reversible. If you can find the path to be reversible path, the heat associated with that path is Q-reversible that can be used directly to this definition. Also, under the assumption or under the behavior that the phase change takes place under constant pressure, then heat can be converted into delta H, right? So we can write this heat, reversible heat, to be delta H of the phase change itself, and delta H of the phase change is called latent heat. So whether it is latent heat of vaporization or latent heat of fusion, still it is latent heat. So we can use this equation, this simple equation, just use latent heat divided by the temperature of the phase change, the transformation temperature, then you can get the change in entropy of the phase change. Reminder that this one is for the system. You still need to calculate delta S of the surrounding before you use the second law. Okay, so once again, this is very important that whenever you rely on the calculation of delta S, if you want to use delta S to determine whether the process is spontaneous or not based on the second law, you will need both delta S of the system and delta S of surrounding. But there is more convenient way for some special circumstance that we can use something else, and then we can consider only the system properties to predict whether the process is spontaneous or not. That parameters is called Gibbs free energy, and we will discuss about Gibbs free energy in the next part of this lecture 2b. So this is the end of lecture 2b, the end of the part 1 of lecture 2b. Thank you for watching.